So, welcome back. We were looking at the method of moments in the previous lecture as a part of the series of estimation methods. We had 3 more methods to go, and the second method in order, if you recall, is the least squares method. We are going to spend some time understanding the least squares method. You must remember that we said least squares method is a really old method, but it is as new as it was about 200 years ago, or more than 200 years ago, because it continues to be used extensively in many applications. The true credit is still not completely decided, but usually least squares method is credited to Gauss. Of course, maybe some historical readings will help you get away from the technicalities of least squares, but the technicalities of least squares is not also so complicated. It is a very simple idea, but works beautifully, and that is why it has stood the test of time and has been applied almost everywhere. Of course, there have been variants of least squares and so on, but we will discuss the vanilla idea, that is the basic idea that is present in least squares, and then leave the rest of the reading to you to read up the variants such as weighted least squares, generalized least squares, partial least squares and so on. So, if you look at the grassroots of this method, it has its roots in the fields of astronomy per se, where the least squares method was proposed to estimate the planetary positions as against Kepler, who was working with a first principles model. And then of course, gradually it has been used in many applications. And if you look at today, it is an indispensable tool in all data driven approaches. It is not a single method or a single data driven exercise where least squares is not used. So, what is this idea of least squares? We will split our discussion into 2 parts. One, we will discuss the basic idea and work out by hand a couple of, at least one example and partially another example, and then we will go to R and see how to implement the least squares. We will not work out the full suite of applications, because remember, when we go to the applications particularly into linear regression, we will use the least squares method quite extensively. At that point in time, you will get to see the more application part of the least squares. For now, we will just show some basic illustrations in R, and we will also use that opportunity to understand how good the estimates are and so on, although we may not have a full fledged discussion. The second part of this discussion on least squares, we will study the properties of the least squares estimators, then where we will ask the question how good are these estimates and so on. Of course, that question has to be accompanied by some more information. We will talk about that later on. For now, let us get started with the generic problem of least squares. And as I had mentioned in one of the previous lectures, in fact, the previous lecture, the least squares method is presented by different people in different ways, and it can also be, it is after all an optimization problem. So, it can be solved also in different ways. Primarily, you will see 2 schools of approaches, or 2 philosophies. One, the statistical approach, and the other is the functional approximation approach. And we will take the functional approximation route, but then gradually move on to the statistical school of thought. In statistics, typically the statements begin by treating the variable for which you are fitting a model, variables for which you are fitting a model as random variables, but we do not have to do that. It is easy to take the functional approximation route, or you can say approximation of a vector and so on. So, what we shall do is, we shall present least squares method as one that gets the best functional approximation for a given signal or a vector. When we say signal, it is not a single observation, it is a collection of observations in time or in space, whatever the independent domain is. And this generic problem is also known as regression in statistics. or linear, where at the moment we will keep the word regression. Depending on what kind of approximation we are seeking, we may run into a linear regression problem or a nonlinear regression problem. All right. So, the least squares method in general when presented is formulated for two different cases. One where you are directly formulating on the observations of the signal, that is you have n observations of a signal, or you can say n observations of a random variable, depending on whether you are approaching from a signal processing or functional approximation viewpoint or a statistics viewpoint. Essentially you have n observations of some variable or a signal, and you can directly formulate the problem in terms of those n observations. Or if you are a statistician, you leave aside the observations and you talk of approximating one random variable using a bunch of another set of random variables without worrying about observation. So, I may have a random variable y, and I may think that this random variable y is can be explained by, let us say, I am not going to use x 1, I will, let us say there is one random variable psi 1, psi 2 and psi p. These are my explanatory variables. There is a nice term that is used. So, I assume that this variable y, for example, if you are looking at let us say thermodynamics, and if you are thinking of the temperature of a gas, you can assume that the temperature of a gas can be explained by the pressure and the volume, and psi 1 becomes a pressure, psi 2 becomes a volume. Or if you are looking at, let us say, relative humidity of the air around you and the temperature. So, you can explain relative humidity using temperature, in which case you have only one explanatory variable, or height and weight, or you can say income of a certain age group. The income depends on, of course, the age, the maybe the stock price of the company for which the person is working, the number of people working in the company, and a few other explanatory variables. So, for you can think of these examples in numerous different domains, and you will find a commonality, and that is why we are looking at the generic problem. The commonality is that you are trying to explain one variable using a bunch of other variables. We are almost at the doors of linear regression or regression, we would say. We are just a few steps away from knocking the door of linear regression. Typically, when we talk of least squares, it is inevitable that we talk of regression. There is no way you can avoid this regression term when you read the literature on least squares. That is why very often linear regression or regression and least squares go hand in hand, because the kind of problems that you solve in least squares, the generic problems, are of the regression type. And what is essentially regression? Trying to explain one variable in terms of the other, and we will spend more time on the word regression later on. Let us get back to the least squares thing. So, the theoretical least squares problem does not concern itself with the observations. It just assumes that there exists a random variable y that can be explained with the help of p other random variables called the explanatory variables, and then the best approximation is sought, and that best approximation is obtained in the least square sense. So, that is a theoretical least squares problem. We will focus on sample least squares problem, so that we directly make this statement. So, let us focus on the problem statement. We have n observations of some variable or a signal, and depending on what you are familiar with, you can think of this variable as temperature, pressure, price of a commodity, or income of a certain person, or it could be height of an individual, it does not matter, right, or the IQ of an individual, does not matter. So, you have n observations of this variable y, and what we are looking at is what we are seeking is the best approximation. You can also use the term prediction. In many domains we use the term prediction, but if you do not find prediction term comfortable, you can use the word approximation. Of this y, whatever you have observed, using m or p explanatory variables. So, we will correct this to p because you have here p. So, we have p explanatory variables, sometimes also called regressors, but for now we will use the term explanatory variables because these are the variables that we hope will explain y. Why do we say approximation? That is what we should keep in mind. We are saying that we want to approximate y using p explanatory variables. Now, the answer is pretty simple. What generates y? So, suppose I look at height of an individual. Typically height is related to weight, but truly is height only related to weight? There are a lot of other biological factors that are responsible for the height, maybe the hormone levels, maybe certain other genetic factors and so on, right. So, there are different factors that contribute to y, among which we would have selected only a subset. It is generally not possible to choose a subset to choose a complete set of explanatory variables for two reasons. One, we may not know the complete set. For example, we may not know what essentially contributes to the height. Is it weight and hormone levels, particular hormone levels and some other biological factors? We may not have a complete list, or that we have a complete list, but we are unable to measure them, all of them. So, typically these p explanatory variables that we have cannot be assumed to fully explain y. If they can fully explain y, nothing like it, but the more general situation is they cannot, and that is why we use the term approximation. So, whenever we try to explain one variable using a bunch of other variables, it is safe to assume that you are approximating and that you are not exactly explaining. Now, given that we have understood why we use the word approximations, we want to construct the approximation in some optimal way, in some best way. Now, that best way in the least squares framework is chosen in such a way that collectively the approximation, what do we mean by collectively here? So, for example, here we have y 0 and then the next one is y 1 up to y n minus 1, or if you do not like this indexing, you can use y 1 to y n. So, we have n observations. What we mean by collectively here is these p explanatory variables that we have, we also have n observation n values of those explanatory variables, each one. So, we have for example, psi 1 0, psi 2 0 up to psi p 0, we have this, and likewise we have another set at k equals 1 and up to k equals n minus 1. Using these p explanatory variables, I obtain y hat of 0. Likewise, at maybe at some third instant, I have psi 1 3, psi 2 3, psi p 3. So, using these explanatory variables, I have y hat of 3 and so on. So, now you can imagine that I have an approximation of y at each instant. And what we mean by collectively is that, let me show you. So, I have here a vector of observations y 0, y 1 up to y n minus 1, or you can run the index from 1 to n, does not matter. We call this a vector of observations y underline, right. In the slides we have a bold faced notation for that. And then we have a vector of approximations or predictions y hat of 0, y hat of 1 up to y hat of n minus 1 at n minus 1. Now, we can build the approximation in many different ways. For example, I can say, since I have p explanatory variables, I can say let the approximation be exact for p observations. So, for example, I can demand that y hat of 0 be equal to y 0, y hat of 1 be equal to y of 1 and so on up to y p minus 1. So, I can force exact explanation for p observations, but typically n is greater than p. Typically, you can say n is greater than or equal to p, but generally we have more observations than the number of unknowns. What are the unknowns? Some p parameters using which we are going to construct this approximation y hat. Now, I have to satisfy all the n observations. What do I mean by satisfy is I want to have best approximation of all the n observations. When n equals p, it is great. I have an exact set of equations, we call that as a determined system. P unknowns, p observations, great. I will have a single solution if it is a linear set of linear approximation, non-linear may be multiple. When n is less than p, I have fewer observations than the p unknowns. I keep talking about these unknowns. What are these unknowns? As I said, suppose I am constructing a linear approximation, that is at each k I assume that the approximation is a linear combination of each of the explanatory variables or the regressors. So, the unknowns that we are referring to are this theta, theta p, theta 1, theta 2 and so on, those are the unknowns. So, from simple linear algebra says that if I have to solve for this p unknowns, I need p equations. So, I need at least p observations to get a unique solution. If I have fewer observations than the number of unknowns, then I have an underdetermined set. That means, I have more parameters, more unknowns than I can actually estimate. Then the other situation is where n is greater than p, and we will generally talk about such situations only, at least in this course. And most of the literature focuses on that. There is a nice set of part of the literature which talks about the underdetermined problems as well. So, when n is greater than p, I can choose to satisfy exactly, that means exactly p equations. In other words, I can drive this error at each observation. Ideally, I would like this to be 0. So, let us define this as a residual. Anyway, we will introduce this terminology a bit later. So, we are looking at a bit ahead into the lecture now, that is okay. So, this we call as a residual or the prediction error also. There is a subtle difference between these two, we will not worry about that difference for now. So, we want this error term, prediction error term, approximation error term or residual term to be ideally 0 at every observation, right. I mean, man when given a chance will ask for anything. So, we will ask for this. But is it possible is a question you must have learnt in many Puranas and epics, the demons asking for immortality, and God says no way, whoever is born has to die. So, this is one of those situations here. There is no way I can get epsilon 0, I cannot get this to be 0 for all k. Unfortunately, this is almost like asking for immortality. No, not possible. You can do this for p observations, not for all observations. But the problem is, then what happens to the error for the n minus p observations? That shoots up, all right. That can shoot up, that is going to be non-zero, because I can with p regressors I can only get error to be 0 at p observations. The n minus p observations will still be the n minus p residuals will still be in error. The least squares approach takes a different stance. It says I am not going to satisfy anyone exactly. I am not going to drive any of the residuals to 0. Remember, this is a completely different approach. One approach is to say I have n residuals, right, corresponding to y minus y hat. If now I subtract y minus y hat, what do I get? I get an epsilon vector, epsilon 0, epsilon 1 up to epsilon n minus 1. What we just said is that it is not possible in general to have all these epsilons, n epsilons to be 0. So, one option as we just discussed is to have any of the p epsilons can be driven to 0, but not all epsilons. That is one approach. The least squares approach first says I am not interested in driving though any of the epsilons necessarily to 0. If that is a solution, so be it, but let us assume that the epsilons in general, that is the number of observations is greater than p and it is not possible to drive all the epsilons to 0, then what is the alternative that I have? It says if you, since in general it is not possible to drive y hat exactly to y for every observation, at least do this for me. What is that? Make sure that collectively those n observations, n approximations are at a minimum distance from this n observations. So, that means something on the residuals, we will talk about that. So, what we are saying is consider this vector y hat and consider this vector y, make sure that the distance, which distance? A Euclidean distance between them, in fact the squared Euclidean distance between them is the minimum. If it so happens in some very nice academic like situation, why I say academic is only in academics, only when instructors solve some very special problems on the board, you will have simple solutions, that is you can drive all the epsilons to 0. That is when there is no error in, there is no noise in your data, your y can be exactly explained by those p observers, explanatory variables and your model is correct. So, when all this happens, then you can have epsilon k to be 0. We know all of this is fiction, at least some of it is not going to happen, right. So, in general y cannot be exactly equal to y hat, but at least make sure y is collectively at a minimum squared distance from y hat, and that is the story of collectively. So, there is so much to think behind that. Okay. So, let us get back now to the discussion that we had. We want now the approximations to be collectively at a minimum squared distance. We will add the squared because distance, Euclidean distance would mean square root from this vector y. So, y hat, in fact there should be no y hat k, it is only y hat, I will make that connection. All right. Now, what are these explanatory variables? Well, it could be any known variable that you think can explain y. They need not be causal variables. So, there is a difference between causal variables and explanatory variables. If you know that physically or sometimes we do not necessarily go by the physics, we say oh that variable has information about y, I am going to include that if I know that. But generally scientifically we would like to have the explanatory variables to be causal variables. All right. So, let us not worry about that. Let us now get into the mechanics of the least squares. Now, until now we have not talked about how we are going to approximate y. Of course, in the previous discussion that we had couple of minutes ago, we pondered over one possible approximation which is a linear approximation. If you follow that, if you use a linear approximation, then we say that we have a linear least squares problem. Although I say when a linear model is used, model is often used as a term for the mapping between y and the Chies, that is explanatory variables that you have. But more importantly, you can think of the approximation. Essentially we are saying y hat is some function of your regressors, y hat at any kth observation is some function of your p regressors or explanatory variables, and if this function is linear, we have a linear least squares problem, and if this function is nonlinear, then we have a nonlinear least squares problem. And there are other variants of least squares as well, depending on how you modify your objective function. Remember we said our we said that we want to keep y hat at a minimum squared distance from y, right. I could slightly change that objective function. Instead of the Euclidean distance, I could use Mahalanobis distance, or I could use some other weighted distance, or maybe I pre-process the data with something prior to using the least squares method and so on. So, depending on what I do, I can have other versions of least squares, but the basic principle remains the same. We will in this course only focus on the linear least squares problem. So, with that note, we shall write now y hat as a linear function of the explanatory variables, just what we wrote earlier. Now, note, take a look at the notation carefully. We are saying there are p regressors, p shi's here, psi I k is the ith regressor, theta is the theta I is the ith parameter, that is the contribution of the pth regressor, and those are unknowns. Rather than saying unknowns, we will say those are our tuning parameters. We are going to tune these thetas in such a way that y hat is placed at a minimum square distance from y. Very often it helps writing this y k as a product of vectors. So, what is this psi transpose? The psi transpose is this vector. First of all, what is psi? By default in our discussions and also in the literature, vectors are column vectors. So, this vector of regressors is essentially a column vector of the individual ones. You must and theta of course is the column vector of parameters given here, and you must verify that dimensionally things are matching. For now, we will assume that the variable that we are looking at is a scalar. At every observation it is just a scalar, temperature, height, income and so on. So, that the psi transpose k times theta should get me a scalar. What is the size of the psi vector? It is p by 1, and theta is also a p by 1. Therefore, psi transpose is going to be 1 by p times p by 1, that gets me a 1 by 1, it is a scalar. So, dimensionally things are commensurate. So, now what is the problem in hand? The problem in hand is that given this is how I am going to approximate y, that is using a linear function, find your thetas or determine your thetas, or you can say optimize your thetas such that the y hat is at a minimum distance from y over your n observations. For this purpose, to be able to write the optimization problem, it is also useful to introduce a matrix of regressors. So, we have started from a scalar, at every observation each regressor is a scalar, and then we introduced the regressor vector, and of course, the parameter vector as well, and now we are introducing the regressor matrix. Do I have to do this to solve the least squares problem? Not necessarily, but it helps us write the optimization problem and the resulting solution in a very nice compact way, and computationally things become easy by introducing these quantities. Otherwise, there is no need. Least squares or Gauss never demanded that you should do this, otherwise you are not your license will be cancelled, and so there is nothing like that. So, look at this is a matrix, and it is good to know the size of this matrix. So, you have psi of 0, remember at each instant the regressor vector is p by 1. So, I have p by 1, p by 1, and I have n such p by 1s, but do not forget the transpose here. So, that now my phi, what is the size of phi? Can you guess? It must be n by p. So, the idea is to be able to write y hat, the collective vector. This is for a single observation at a single instant in time. For the entire set of observations, we can now write y hat equals phi theta. So, you see it is a nice matrix form, a linear operation. We know phi, we do not know theta, we have to determine theta. We will also use frequently this term z, but not frequently, sometimes, which is the union. When we say union, not addition, just collectively as a package your observations and your regressors. So, that is what we mean by z here. It is a collection of the observations as well as the regressor matrix. So, now the optimization problem that we have, what is the optimization problem that we have? We want to minimize this objective function. So, we say j, it is a function of theta, this runs from 0 to n minus 1 or 1 to n, and we want to minimize the sum square errors. That is why the name least squares. So, we say the minimize this with respect to theta. This is the least squares optimization problem. The same optimization problem now can be written in terms of the vectors and the matrices that we just introduced. So, for those of you who at least have some basic exposure to elementary vector algebra, and if you do not, you can just read up a book, it just takes about 5-10 minutes. You should recognize that this sum square can be written as the squared 2 norm of y minus y hat. Okay. What is squared? First of all, what is y minus y hat? Y minus y hat is nothing but your residual vector. Remember, we defined this residual vector already. So, what is the size of this? The size of y is n by 1, size of approximation is also n by 1, epsilon is also n by 1. So, we have now what we are saying is this sum square here that you notice can be written as the squared 2 norm of epsilon vector. What is a square 2 norm of a vector? I leave it to you to figure out. It is a very, very easy quantity, just one click of a mouse or tap on your phone with the keywords 2 norm of a vector will get you the answer, and then you will understand how we are able to write the sum square as a square 2 norm of a vector. Simple exercise. We can also write square 2 norm as a product of the transpose of that vector times itself. In other words, I can write this as epsilon transpose epsilon, that is also possible. Fine. So, I have written it this way in this optimization as this problem, because this is a standard way in which optimization problems are written. Of course, you can still simplify directly and say minimize here y minus, you can in certain textbooks you will see y minus phi theta transpose times y minus phi theta, find theta. So, you can say this n is to indicate that I have n observations. Sometimes you may also see a 1 over n here in certain textbooks, but that does not change the solution at all. It only changes the value of the objective function, scales it, but does not change the solution by any way.